we continue our discussion on centrality. So, the question where we ended in the last class was, suppose you are given the hyperlink structure of the internet, or sorry, the web. So, that is the network we are talking of, and we are asked to find the relevance of a or the popularity of a page. So, popularity might mean many things. It might mean which particular web pages are more authoritative in the sense that they have more valid information, you can trust on them, and so on. And we saw that degree centrality, betweenness centrality, or closeness centrality does not help us completely. So, we have to find some new measure, and you had a suggestion for that new measure. The suggestion was based on this very basic idea that if I am popular, if my friends are also popular. So, if I have all my friends who are really popular, then I am also popular. In other words, if in the case of the web pages, it translates to, if authoritative or popular web pages link to me, point towards me, then I am also a very popular or authoritative web page. That is the intuition behind it, and you all intuitively came up with this idea. The problem was that given a network, how to compute such a notion, how to define this notion mathematically, and how to carry on the computation. So, one of the suggestions that came is actually very elegant and simple. What it says is, suppose we want to compute the centrality of this particular node, the popularity I would call it, of this particular node 6. What we do is, we say that the popularity of the node 6 is sum of the nodes P2, the popularities of the nodes 2, which is P2, 5, 7 and 8, basically the nodes which connect to this particular node. Note that this particular example I am working out is with an undirected network. Web is a directed network, but friendship network is a undirected network. So, just think that I am trying to calculate the popularity of each of these persons in this particular friendship network, and I say that the popularity of a particular person, say person 6, depends on what is the popularity of his or her friends, here 2, 5, 8 and 7. So, this is for 6. Likewise, we can define for 5. So, what will be P5? P5 will be P6 plus P8 plus P7, and in this way we can define. But the problem is, as we encountered, how to start these values of, how to initialize these values of P1 to P8. We have to first initialize and then iterate, and we have questions like, if we do this process, will it converge, if it or should we stop at a particular number of iterations, and all this. So, let us do some hands-on experiments and see what happens. So, suppose it is the simplest thing, right. Let us initialize all of them to the same number, say all of them have popularity 1 to start with. So, what happens in the next iteration? So, this particular node now gets popularity value 2, because one of its neighbor has 1, one of its neighbor has 1, and 1 plus 1 is 2. What about this? It has 4 neighbors, all of them is 1, it gets 4. So, likewise you can compute for all the nodes the popularity values, and you get this particular network. Now, we start with this particular network and then iterate the same process. What will happen? So, this now gets a popularity value of 6, because this is 4 and this is 2, 4 plus 2 6, and this particular node, say 4, which was earlier 4, now gets 4 plus 3 plus 3 plus 3, which is 13, and in this way it is getting the values. But do you see the problem? What happens if we continue to iterate in this way? It keeps on increasing without any bound, right. We really do not know where to stop, and the values, the absolute values of the popularity really will depend on, after how many iterations we will stop, and these values are increasing really fast, because it's like almost a geometric progression. It's sum of other values of the same magnitude. So it looks like that popularity is in this model is growing unboundedly. Now this is something which all of us will really want to, but unfortunately that never happens in real life. So it's something which is not practical in terms of computation and in the sense of, you know, how it really goes on in real life. So there should be some bound. So can you think of a way where how we can bound these popularity values? Right. So what he is saying is we can normalize the popularity values after each iteration. So by normalization we might mean several things. The simplest way of normalization is enforce the sum of the popularity values of all nodes to be some value. Here we have chosen it to be 1. So we have chosen it to be 1, and we know that our initialization condition is we give same weightage to all the nodes. So naturally all the nodes now get, since there are 8 nodes, all of them get 1 by 8 in the first step. What happens in the next step? So actually the same values like we saw earlier, like 2, 2, 4, 3, remember these are the earlier values also, because you are adding 1 by 8 plus 1 by 8, you get 2 by 8 and so on. But then sum of these values, say 2 by 8 plus 2 by 8 plus 4 by 8 itself is 1. So 3 by 8, it's more than 1, but we have constrained it to 1. So we have to divide it, normalize it. So what should be the value with which we should normalize? So we sum them up all, and the sum will be like 2 plus 2 plus 3 plus 4, 1, 4, 3, 3, which is 22. So basically we have to divide it by 22 by 8, effectively multiplying 8 by 22, 8 8 cancels out. So essentially what happens is all the nodes will be now divided by 22. So this is 2 by 22, this is 4 by 22 and so on. So this is after your second iteration. Now you start with this network and repeat the same process. Now these are the values that you get. Again you have to normalize. So the normalization would be, again sum them up, 6 plus all, I think it turns out to be something like 68, and so you normalize it, so 6 by 68 and all. So you get this, and now you start with this network, again do the same thing. So now these are the new values. So this node gets 9 plus 10 plus 10, which is 29, 33, 33, sorry, which is 39, and it's still 68, but after normalization now the denominator becomes 206. Yes?
There's a flaw in this method.
Yes.
The values that we are getting is not just unique to the structure of the network. It also depends on the way you are traversing the network.
No, we are not traversing the network in any direction here. It's just at every point of time, it's the sum of the weights of the neighbors. So there is no directionality or ordering.
When you started with 1,
It might depend on the initialization. We will come to that we started with 1 for all the nodes. We might start with some other values and we might have ended up in completely a different set of values. So that's true. We still don't know whether initialization affects or not. But suppose we take the most naive case, we assume that all the nodes have same popularity to start with. We are really fair. We don't give extra privilege to anybody to start with, and we continue the process. We want to see where it goes and if at all it converges. So what do you think? Is it converging? So to see that, these are the last values that we got after 4 iterations, and this is just actually for your reference to tell you the node numbers. This is 1, 2 and all this. Let's see some how each of these sequences of values for each of these nodes are changing. So if you look at, say, node number 1, that is this node, we started with 1 by 8, then it went to 2 by 22, 6 by 68 and 15 by 206. The latest is 15 by 206. So it's not so easy to really understand whether it's growing, decreasing or what. So if you look at these figures, we have just removed the fraction and represented it as in decimal. It shows it might be easier to compare. So what happens is it started from a large value and it's slowly decreasing. Okay. Whereas this one, you see, it started from a small value but it's interesting, it's node 2 actually. We are looking at this node and it's actually oscillating, but even then it's higher than where it started from. So it went, jumped, and then again dropped, then again jumped, and actually it will oscillate. So although it's not absolutely clear from this small 4 iterations that it is going to converge, but I think most of you can get the feel that it is slowly going somewhere. And this oscillation, actually if you see this amplitude of oscillation is decreasing. So it was 0.125, from which 0.182, which is really 0.06, then it's like 0.05, then it's 0.01. So the amplitude is dampening. So slowly it's going somewhere, right? And similarly, this value is decreasing, but might get to 0, but doesn't seem like from the trend, because again here also the differences are not that diminishing slowly. So seems like it actually is converging. And the good news is, if you really do it for a sufficiently long time, then indeed these popularity values will converge. If you start from this particular uniform thing, and if you restrict that sum should always be 1, they will converge. And I don't know if you have noted another thing, which I call that nodes which are isomorphic have the same popularity value. So just look at, say, look at this node 1 and 4. If you rename 4 by 1 and 1 by 4 and vice versa, the structure of the network remains exactly the same, right? It will not change. Can you see that? So these two nodes are isomorphic. If you see throughout the computation, they have the same value for popularity. This is 15 by 206, and if you look at the previous iterations also, in every iteration they have the same values of popularity. Actually it's very easy to see that they will have the same values of popularity, because all their neighbors are same, right? They are isomorphic because this is connected to, so both of them are connected to 2, and of course to each other. So the nodes, so there are these two interesting things about this particular measure that we have come across. One is that it eventually converges, at least for this network that we know of, and the isomorphic nodes have the same popularity value, which is really an important property, because we really want the nodes which have very similar link structure should have the same values. Now, but the question remains, what happens when we start from a different initialization condition? And what do you think? Well, if we have the restriction that this sum should be constant, need not be 1, it can be n, doesn't matter, but that n should be constant, and we always normalize it with respect to n, and we start from very different initialization conditions, for this particular network it will always come to the same point. We will prove this mathematically why so. It will always come to the same point, but actually that's not a general case. There will be networks, actually there are networks where you start from a different initial condition and you end up in different set of eigenvalues, you end up in a different set of popularity values. But for this particular network, so what's that interesting property of the network for which initialization doesn't matter? I don't expect you to answer. If you can answer, that's excellent, but we will see. So that was what I essentially was telling. Does it converge for every graph? One question. And does it converge for all initial conditions in the same way? But we will come back to these questions when we will later on when we will do some mathematics. This is also another interesting question. What happens for a disconnected graph? But we will come back to all these questions. But before that, let's look at an alternative view to popularity. So here we said, if my friend is popular, I am also popular. But think of another very different model. We call it the random surfer model. It makes really sense for the web. So think of a person whom we will call the random surfer, who lands up on a random page, an arbitrary page on the net. and then from that page with a particular probability, say probability W, the random surfer stays in that page and moves nowhere, and with another probability, say 1 minus W, with rest of the probability, it goes to one of the random links. So, what it would mean is, suppose W is 0.5 and the random surfer suddenly lands up on page 2. Then with probability 0.5 it will remain on page 2, and with probability 0.5 it will move out of this page 2, but it can move to actually page 1, 4, 6 or 3. The probability that it will move to page 1 is 0.5 by 4. There are 4 pages, and with probability 0.5 it moves to any of them. So, to each of them it is like 0.5 by 4. So, it can move to this and so on, all these pages. So, this is a random surfer, and the question that we are asking here is, was the probability that after sufficient number of these clicks, this random surfer is clicking, right, he is staying for some time and then clicking and then going to another page, and so what is the probability that the surfer ends up in a particular page ultimately? And what I tell you is, this problem and the previous definition are very much related. So, think of 1 by 8s in the previous problem. Since there were 8 nodes, the random surfer can end up in any of the nodes. So, what 1 by 8 was meaning there is the probability that he is in node 1 or node 2 or node 3 and so on. So, all of them gets uniform probability, he starts from anywhere, and then from each node, say from 2, the probability that the surfer goes here, or rather we looked at it from the other direction. Say the probability that the random surfer comes to page 6 is only possible if the random surfer is at 2 or is at 5 or is at 8 or is at 7. So, that is why we add their probabilities actually multiplied by the factor that if it was in 2, then it should choose this edge and so on. So, those details we will work out to show that it is exactly the same or very similar, but this is basically the model. So, a very different view to popularity in the case of at least the web is that you are doing a random walk. This is called a random walk. You start from any node and you randomly choose one of the edges and go. So, what is the probability that after walking for say 1000 steps or 10,000 steps or billion steps, basically it's called also time, as time goes on you are walking through the network, what is the probability that you end at certain node. Okay. Now, there is also another. Okay. So, before going to that interesting thing I was going to tell you, let us see the equation. Equation is again very simple. The same equation actually, the probability that you are at P6 at a particular time depends on again P6 at the previous time. I have not subscripted. So, the right hand side is the one step before and the left hand side is one step after. So, you were in P6 and of course, with probability W, and then with 1 minus W you can come to 6 either from P2. So, in the previous step you were in P2, its probability is P2 of course, and you divide it by 4 because from 2 you can go to 4 pages, right, 4 different pages. So, you get this point why we divide it by 4, everybody clear? This is important. So, we basically we are dividing it by what of the node? The out degree of the node. So, we are dividing it by the out degree of the node for each of the nodes. So, P5 out degree is 1, P7 out degree is 3 and so on, P8 is again 1. So, oops sorry, yeah, so it will be by 2. So, in this way we can define the equation. One interesting thing for random walk is that when you are at a particular node, the probability that you will end up in some other node does not depend on how which path you chose to came to this node, right. It depends only on the fact that you are at this node at this point. So, suppose you are at node 1, what will happen in the next step? You have nowhere to go, right, you have to be at node 1. So, does not matter through whichever path you came to node 1, your future is determined only by the fact that you are at node 1 at this point of time. Alternatively, think of again, say if you are at node 6 at this point, you can only go to 8 or 7, but it really does not matter from where you came to node 6. The history does not matter, and any process in which the history does not matter, you just look at the previous state and take the decision, is called a Markov process. So, random walk is a Markov process, and actually we will see that all these things are related. This notion of popularity of centrality is related to the Markov process of random walk on a network, and which again is related to something which we call the eigenvector, the principal eigenvector of the graph. But how it relates to the eigenvector we will come to in a moment. So, we ask the question, what is the probability that the surfer is at node I? So, we can write it in this way, right? The probability that the surfer is at node I depends on some factor w and the probability that it was at node I in the previous step, or with 1 minus w it has come to I from some node j. In that case, there should be an edge between j and I. So, what is AJI? Is the adjacency matrix representation. You got that point? I will show you just in a moment, multiplied by the probability of being at particular node j and divided by the out degree of j.
What is W?
W is a some factor of being staying in the same node and not progressing. It's some factor to the random walk. We will see how does it matter, if at all.
That we are taking care of by PI itself.
You are taking care of?
How do W and PI differ?
Oh, so PI is basically that you were, the probability that you were on this node previously, right? And W is telling, so if you look at the graph, what W is telling is there is a self loop here. You can, from this node you can remain in this node. So you can think of it also as an inertia or as a self loop, and the weight of that loop is W. So from this node you remain in this node.
How do we guess W?
You need not guess W, we will see what happens. So with a given W we will end up somewhere, and we will see with different W's it might change and so on. But before that, let us just clarify this particular thing, which is AJI. So what is AJI? So say here we have the columns are marked by the 8 nodes, it is the adjacency matrix representation. So 1 is connected to none of the nodes, means no edge goes, and from 2 there is 1 edge to 1 and 1 edge to 4 and 1 edge to 3 and 1 edge to 6. So in those places we make it 1 and rest of the places 0. In this way you can fill the whole matrix. It is nothing but the adjacency matrix representation for this graph. It is clear, right? Okay. If this is clear, then we will do some computation, further computation on this. So we said Pi is equal to sum W Pi sigma over all j. There is an edge from j to I. If there is no edge, this value will be 0. So basically you are not multiplying the probability by dj, which is the out degree of the node j. Okay. Now instead of Pi, I can write this equation as P1, P2, P3, P8 in the general case, Pn, and all of them will be written in this way. And so on. Okay. So all these equations we can write in this way. So we can make a compact representation. Let's call this P1, P2, P3, Pn as the vector. It's a vector, right? It's a column vector. So, let's call it the vector P of these probabilities. Then this vector is again P1, P2, Pn, this is the vector P, right, but it's at time t plus 1, iteration t plus 1, and it's at iteration t, plus 1 minus w. How can you write this one? Can you write this as a, you know, matrix multiplication? Let's see. Again, this is P1, P2, Pn, okay, and here I might write it as in this way, A11 by D1, A12 by D1, and so on. D1 is nothing but this summation of A11, A12, and so on up to A1 n by D1, right. Similarly, this is A21. So, there is an edge from 2 to 1 by D2, A22 by D2, and so on. And can you see that this is what comes like when, so P1 gets multiplied to A11, P2 gets multiplied to this, and so on. However, A11, A22 are by definition all, oh sorry, is visible? Yep. So, can you tell me what is A11, A22 and all these values for the networks? All are zeros, right, because we are not considering self loops. Okay. And what is this matrix? This is the adjacency matrix divided by this adjacent this D1, D and D2s and so on. So, we can write it in this way. Let us call it some A normalized, because we have normalized each of the rows dividing it by the degree, and it is also PT. Up to this it is clear? Okay. If it is clear, then, so let me rewrite again. I have just taken PT out of it. Actually, this whole matrix, whatever is here, I can represent it as some transformation of A. Let us call it AL. So, what is the transformation actually that we are doing? Let us see. So, we had the adjacency matrix. In place of 0, we have put W in the diagonal, because W is multiplied by the identity matrix I. So, basically all the diagonal entries are W, and these entries are all A12 by D1 and so on into W minus 1, right, because of this, sorry, 1 minus W, because of this 1 minus W. So, this is the matrix, and for which, so let us call it the AL matrix. So, this is a slight transformation of the adjacency matrix. We are dividing each of the rows, and then after dividing each of the rows by degree, we are also multiplying it by 1 minus W, rest of the columns, and this column as W. So, ultimately we end up in the equation, in an equation which is like this, right. So, does it remind you of something? when does it converge? At the convergence point we should have P is equal to, right, this is the point when it converges. If you iterate, even multiply with AL, it remains AL, sorry, it remains P, it continuously remains at the same point. So this is the most crucial equation. So all kind of Markov chains, there might be variations, like W might be 0, and you know, you can play around with it a little bit. If you look at, you know, different books, you will find slightly different kind of approaches, but ultimately you will get an equation of this form. And what it tells you directly is that P should be an eigenvector of AL, and then what should be the eigenvalue? What is the eigenvalue? Exactly. So the equation is what? Ax is equal to lambda x. So L lambda is 1. So now tell me, what if L doesn't have an eigenvalue equal to 1? What will happen? So the convergence only holds if L has an eigenvalue equal to 1. What if L doesn't have an eigenvalue equal to 1? It doesn't converge. Okay. So actually there is a theorem, we will come to that, but before that, okay, it's very clear that then popularity, all these algorithms, what we are doing is a kind of centrality which is the eigenvector, which is also called the eigenvector centrality, because this P here, which is the popularity vector, is nothing but the eigenvector, right, for eigenvalue 1, and that particular eigenvector gives you the eigenvector centrality. But we are left with two questions. One was, does it have an eigenvalue 1, and even if it does have an eigenvalue 1, is P unique, is the eigenvector unique? So what does the normal matrix algebra, the linear algebra, tell you? So one thing is, any multiple of P is also an eigenvector of P, right? So if P is an eigenvector, and you know, K is a scalar, then Kp is also an eigenvector. So that's why now, you know, can you guess like why we need the normalization? Because even if it converges, this K diverges. It will converge in the direction of the vector, but it will diverge. This particular value K will diverge, and you will have bigger and bigger kind of multiples of, means bigger versions of that particular vector. However, if we restrict P, so how we restricted P? Our restriction was add the sum, add the component values, and that should be fixed at 1. That's how we restricted it. There are other ways of restricting. So the most popular way of restricting a vector is it's restricting its length. So you might say that the length of P should be 1. In that case, the sum of the components should not be 1. What should be 1? The sum of the squares of the component should be 1, because you are saying this particular vector should be of length 1. Is it clear? It's not clear? Okay. So what did we say to start with? We wanted to find this P, P1, P2 and P3 and all, and subjected to the constraint, we had several constraints, and one constraint was sigma Pi equal to 1. That's why we renormalized again and again, right? After every iteration, we ensured that we are choosing that particular vector for which the sum is 1. But this is one way of normalizing, of course, and it works, but there is another way of normalizing, and that is called the actually normalizing the length of the vector. So this, what is the length of this vector P? Suppose there is a vector which is like P1, P2, these are the components, say Pn. What is the length of this vector? It is simply right. So I am just doing Pi dot Pi. square and you do a root of this. So, this is the length of this vector. So, we could also restrict the length. We could have said that the length of P should be 1. In that case, our normalization term is sum of squares, because if this is 1, then the term inside the square root should also be 1. So, sum of squares should be 1. Such vectors are called unit vectors, because its length is 1. So, we saw that it is the eigenvector, and it is the eigenvector corresponding to the eigenvalue 1, but we are still not sure of many questions. So, one is does it always have an eigenvalue 1, and the second is, if it has an eigenvalue 1, is the vector unique. The vector is unique subjected to its length is fixed and so on, but even then will be the vector unique. If we have this constraint, even then will be the vector unique. Suppose it has eigenvalue 1. Think. Actually not. The eigenvector will still not be unique if the matrix has multiple eigenvalues which are 1. So, a matrix can have a repeated eigenvalue, right? It can have an eigenvalue 1, it can have 2 eigenvalues which are 1, and corresponding to those 2 eigenvalues it can have 2 different such vectors, principal eigenvectors. So, there are all these issues, and we will take some of them of course, but before that, so this is a very old concept actually in network theory. It was
Sir, you said about normalizing the vector in each step. So if we normalize the vector in each step, that means we are changing the matrix KL in each step, right? So in that case, what do we say about the eigenvector? We are changing the matrix in each step, so its eigenvector will also be changing. I mean, the analysis is not clear enough.
in the previous case.
I mean, if
So-
we keep normalizing after each step, we'll end up changing the matrix in each step, and so the analysis will not hold.
Right. So actually you are not changing the matrix, right? What you are essentially changing is you are keeping the length of the vector also, the direction of the vector also constant. You are just changing the length of the vector by normalizing. So you are taking all the values and dividing it by a particular sum of the values. So basically you are changing the length of the vector, but you are not changing the direction of the vector by doing that process.
If we do that, then even eigenvectors which have eigenvalues different from 1 will also solve our purpose, right?
No, it won't solve your purpose. Think of the equation. You have P on both the sides. I think you have forgot that. So if you normalize this side by some x, you have to normalize this side also. So the normalization goes on both sides. Therefore, it doesn't affect lambda. Got the point? So suppose you could say, what if I multiply P by -1? So I see the vector in the negative direction. Actually, you can do that. Actually, that will not change lambda to minus lambda, right? Because actually what is happening is you are getting minus sign on both the sides, but lambda remains fixed. So therefore, whatever normalization is taking place on this iteration carries on to the next iteration, right? So in the equation, it's affected on both the sides, not only just your RHS. So that's why it doesn't means the ultimately the steady state is the same. Okay. So it was kind of introduced in 72 by Bonakish, and before we go on to some of these interesting questions that we asked, let me also just mention that all of you must have heard of PageRank, Google PageRank. So which is used to kind of rank the pages over the web. So that's the problem we started with actually. We wanted to find out pages which are more important, and the PageRank algorithm, just go and check it out. It's very similar to this algorithm that I presented. There is a slight difference. Instead of this W, they have a dampening factor D, and they don't multiply with Pi. So basically this AL, ultimately the matrix AL that we got here will be slightly different. Remember, we ultimately said it's this. They do some slightly different computation on the adjacency matrix. So that's why it's slightly different, but more or less it's comes down to the eigenvector centrality. So it's like this equation. Here you don't have pi multiplied here. So coming back to our very interesting question, does all networks have lambda equal to 1? This AL for all the networks, does it have lambda equal to 1? And it turns out that yes, it is the case. All networks will have at least one eigenvector which is equal to 1. The network, by network I mean this AL, the modified adjacency matrix. So can you tell me what's so nice about this modified adjacency matrix? What are the properties, nice properties that you can think of this adjacency matrix, that this modified matrix called AL? If you constant and equal to what? Equal to 1. So just check it out. So this is W and this is A11, sorry, A12 by D1, 1 minus W into A2, sorry, 13 by D1 and so on. So if you add all these terms, what will it come to? 1 minus W, and plus W you have 1. So all the rows sum to 1. This is one nice property of this matrix, and such matrices have a name called, remember this name, row stochastic matrix. Why it's stochastic? Because if the sum of the rows is equal to 1, you can interpret them as probabilities. So therefore it's called a row stochastic matrix. You could have a column stochastic matrix also, where the sum of the columns are 1. You could have a doubly stochastic matrix, sum of the rows as well as sum of the columns are 1. All of them have very nice properties. Actually row and column stochastic matrix are very close to each other. If you can convert a row stochastic matrix to column stochastic matrix by taking its transpose. So and eigenvalues of the transpose matrix remain the same as the original matrix, although eigenvectors might change. So this gives you alternative formulations, and in some books you can see they use row stochastic matrix to derive, sorry, column stochastic matrix to derive the same thing, but not a row stochastic matrix. There is another name for such matrices actually, and that's called a Markovian matrix, Markov. And why it's called a Markovian matrix? Because it represents a Markov chain. Basically every matrix, this kind of an equation represents a set of linear equations, right? And all these linear equations can actually represent a recurrence relation of a Markovian process. So it's a Markovian process because sum of the right hand side, these values are all interpreted as probabilities, and then you multiply with the previous state, which is the vector p, and you get the fresh probability distribution. So it depends only on the previous iteration, and therefore it's called a Markov matrix because it represents a Markov chain. If time permits, later on, not in this lecture, we will see the details of how we can do interesting computations using eigenvalues and eigenvectors for Markov matrices. But what it turns out is that all of them have a value, eigenvalue 1, because they are all stochastic matrices. I will not prove the theorem, I will give you references. You can look at Gilbert and Strang, Gilbert Strang, a book on linear algebra. I have a copy, I can give you the full reference, and you can look at the proof there. It's slightly involved, you have to do prove some basic lemmas before you go there, but this is one theorem which is really useful. And there is also another interesting property of this matrix. It's actually very trivial, so you might have missed it. Apart from the fact that the sum of every row is 1, what else needs to be enforced for all of them to be interpreted as probabilities? Right. So all of them should be non-negative, greater than equal to 0. So, such matrices are called positive matrices. So, this is not only a row stochastic matrix, this is also a positive matrix. And actually these two together leads to the fact that this will have one eigenvalue lambda 1, the highest eigenvalue actually, which will be equal to 1, and the eigenvector corresponding to it will be the principal eigenvector, because so I guess you know the principal eigenvalue and principal eigenvector. The largest one is called the principal eigenvalue and the corresponding eigenvector is the principal eigenvector. So, you can also note down this theorem which actually closely relates to this whole exercise. It is called Perron-Frobenius theorem. What it says is, if A is a positive matrix, for any positive matrix, need not be a stochastic matrix, just a positive matrix, then its largest eigenvalue lambda 1 is positive and actually greater than the absolute value of all the other eigenvalues. That is what it is saying. And not only that, every component of the corresponding eigenvector is also positive. The corresponding principal eigenvector is also positive. So, again I am not going into the proof of Perron-Frobenius theorem, it holds for every positive matrix. So, there are two parts of it. One is lambda 1, the largest eigenvalue is positive and greater than all the other eigenvalues, and actually lambda 1 is called the spectral radius. It is called the spectral radius of the graph. We will go into those definitions tomorrow. However, the more interesting part is that the corresponding eigenvector has also all positive values. Now, let me come to the other question that we left out. Does it work if we start from any random initialization? Does it really converge? Because we saw at steady state actually the recurrence relation holds. So, what we have proved is actually if P is the eigenvector of the AL, then this equation holds. This is the steady state. This is what we have proved. But actually we are not computing the eigenvalue directly. What we are doing is this. We start with some random P0, which is in this case the uniform assignment, but think of any random assignment, and we are multiplying by AL to get P1. What is P2? AL times P1, right, which is AL squared times P0. If we continue this, so what is like some Pn? So, then Pn will converge if irrespective of what is P0, this particular matrix actually has a fixed value. Again, you look at I am just giving you very sketchy idea of why it happens. Since it is a stochastic matrix, if you do powering, only some prominent terms will be left out, and if you multiply two values which are less than 1, the values will get smaller and smaller. So, most of the values will get smaller and only certain values in this whole matrix will dominate. So, in this way by powering it turns out you can get to the eigenvector. It is called the powering method. You can get to the principal eigenvector starting from any P0, subjected to only one constraint, that this P0 cannot be orthogonal to the original vector, means orthogonal to the eigenvector. You want to come to finally something called say P star. So, it should be orthogonal, it cannot be orthogonal to P star. So, how do you ensure when you do your assignment that it is not orthogonal to P star? This you should be able to answer. Right. So, did you get his point? By Perron-Frobenius theorem, we already know that P star has all positive values. All the components of P star is either all positive, or if you multiply by -1, all of them will be negative, but all of them have same sign. So, if you choose P0 such that all the components, all the initial values have the same sign, then multiplying P0 with P star can never give you 0, right, because either all of them will be positive or all the values will be negative, they cannot cancel out. So, you can start with any P0 with all the values positive. So, the uniform one works, the degree one works, or some other assignments also work, The only thing is you have to ensure that all of them are positive, and another thing is, again I am not going into the details of that, for particular kind of assignments your computation might be fast, your convergence might be fast. So, you need not go to higher powers, you need not multiply AL with AL for a long time, and you can do it faster. And as you can already see, there is one very easy method to compute the eigenvector centrality. It is like you take the matrix, adjacency matrix A, convert it to AL and do powering. Okay. And for powering you have again very fast algorithms for matrix multiplication. So, this is one way by which you can compute the eigenvector centrality. It is called the holding method. Okay. So, that is all we had on centrality measures. Tomorrow we will see some problems with the PageRank algorithm and its extension, which is called the Hitz algorithm. We will discuss those algorithms tomorrow, and also we will try to look at some of the interesting matrix algebra thing, eigenvalues and eigenvectors you can play around with, so that it will tell you interesting things about the network. Okay.